Calculus, introduction to calculus. Let's start there. Okay, this is the introduction to calculus. Let's not start with the 1, let's do something a bit harder than that.
4.
What does that equal?
1.
Right. It might do, yeah, if it was, yeah, could have been. What's this equal? 6. That's it then, you can do calculus. Well done. So we can go home now, doesn't it? So basically, if you can do simple maths like that, you can do the large majority of what we're going to do with calculus. There's a little bit more to it, it gets obviously gets more advanced. We'll come back to that though. So that's your first point, it's easy. Okay, what is it? Let's start with what is calculus, what does it mean? Well, there's 2 types of calculus, main types that we're going to be using.
We're not using formulas, are we?
Not a lot of formulas, no.
Oh God, I don't use formulas.
There are some formulas used in calculus for things like for finding the mean of an area and things like this that we will come to. They're not difficult formulas, in actual fact. Calculus is not. The thing in calculus that's difficult is doing the maths parts, and it's quite easy. Okay, what is it though? Well, there's 2 types. There's differentiation and there's integration. So, are you listening? Yeah. So there's differentiation and there's integration. We're going to cover those 2 things. They're the main areas, divides of it. They're both connected. We'll come to this more as we go through it. But calculus is going, differentiation is going forwards and integration is going backwards. But it's really clever how they both get used, as we'll see as we go on. So differentiation, we'll start there. What is it? If you've got a straight line like that, right, I hope you all know how to find the gradient for that straight line. And the formula, you know the general formula for this?
Yeah, the gradient, yeah. You find one point, you measure it.
Yeah.
Just an example there.
And another point.
Y equals blah blah blah.
And then you make a triangle.
Yeah, you can make a triangle. That's often the way that it's done. Really what you're doing though is you're taking these values down. This is your x-axis. This is y-axis. And you're taking these values across to here. Okay?
And then how do you work it out again once you go to
Right, well the gradient is to do with how steep it is, obviously.
Yeah.
You walk up a hill, you know.
Oh,
You live in Bradford, you know about
I know how you
gradients.
do it. You work it from one part, bottom part of the triangle, and then you go up in it.
Yeah, well, it's basically what we're looking for. The where triangle comes in. You don't actually need the triangle, you just need to take these points across and down to where they touch the x-axis and the y-axis.
Yeah.
And this gives you x1, this gives you x2, this is y2, and this is y1. And it's about, remember, have you heard the saying rise over run? How much it climbs in how long, what the distance. Very logical. If you walk up a hill and you climb up 10 metres of height, if it's a long way, then you don't notice any gradient. And if it's a short, steep, 10 metres, it's 45 degrees, isn't it? It's very steep. You need steps then probably. So basically, it's the change from here, to here, divided by the change from here to here, and that gives you the gradient. You remember the general formula for the straight line? You remember this?
Y equals mx plus c.
Yeah. You remember what the c is?
The difference, like how up you go on that cross point.
That's right, the cross point. Where it crosses the y-intercept we call it.
Yeah.
So that's your c, and your m is the gradient. Yeah. So if I'm looking for the change from here to here, divided by the change from here to here, the formula for m would be y2 minus y1 divided by x2
Minus x1.
Okay? So it's that change there divided by that change there, that gives you the gradient. Now, does it have to be big, so to speak? Do I have to have big x1 and x2s, or could I have them really close together? Could I have my x2 here? Could I have a little small triangle, for example?
Yeah.
Does it make it Did it make it any different?
No.
No, because it's a straight line, the gradient's the same. So I can make it really, really small if I wanted. If I zoomed in, if this was in software and I zoomed in and got make it really, really big, then I can get closer and closer, can't I? And that principle is where we're going to come to in a minute with calculus. That's what calculus does. Right, that's easy to do. You can plot it on a graph or just get your maths and do it, and you'll get the gradient, and that you would substitute that into there, substitute where it crosses that line into there, and you've got a formula, and you can work out any value for y for any value of x on to infinity and minus infinity. Okay? Right, that's easy. What about this one? What I need to say actually is what differentiation is all about finding the gradient. How steep is that hill? How steep is that slope? That's what it's all about. Now it's easy with a straight line. What about if we have x squared? Okay. Yeah, then we get a curve shape, don't we? Yeah, it starts something like this and goes up and goes up, and it keeps going up and up, but never gets vertical, even if you get to infinity. Well, if you get to infinity, it does, but obviously we can't get to infinity because there's always another number after infinity. Infinity plus 1. So it keeps going up to infinity. I can't do an infinity symbol now. I just can't do it. It's what come with it. Right. Infinity. Yeah, 8 on this side.
Is like the Virgin Media thing in it?
I've done it loads of times. Yeah. I've done it loads of times.
Yeah,
So,
it's easy. Just do this. Okay.
So y equals x squared. Right then. What's the gradient of that? How steep is that slope?
Very steep.
Well, it's not down here though, is it? It's nearly flat there.
Yeah.
But there it's very steep. So if I wanted to find out what the gradient was, say I say a value of x here, let's call it question mark x. Okay. So it's some value of x there. 2, 3, 4, a billion, whatever. How would I find that gradient at that point there?
You'd have to go across here back to the thingy.
Well, yes, but we need another value, don't we? Remember before we had to have 2 values.
Yeah, just do another one a bit further on.
That's it, basically. You'd have either put another one, that's a good point about putting in another one. If you try and get it closer, it gets more accurate. Or you can do where you try to guess the gradient by putting your line of best fit on.
Oh yeah.
So you know, zooming in sort of thing, you've got this shape, you try to guess that it's at this point it's something like that. And if we all did that, if we all had a piece of graph paper with that x squared, we'd all be different, yeah. So you'd get your 2 points on that line and do the same process, but you'd all get different answers. Now, what a couple of famous scientists, one of them you've definitely heard of, the other one you might not have heard of, they came up with a solution to this problem. Because obviously that's inaccurate, and you want to do it, you've got to find it for every different place, every different value of x. So you've got to start again, putting your line on, doing your calculations. So they came up with a solution. So one of these guys is Isaac Newton, that you've heard of, I'm sure.
Yeah.
Okay. One of the great scientists. Another one is another great scientist, mathematician that you might not have heard of, a guy called Leibniz.
I have heard him.
They came up with this method independently of one another, and they worked out the maths from first principles. And what they said was, let's call this P. Okay, now somebody there said about putting another point on, you can put it on the line, so let's put it here. They call this a chord. Okay, you draw a straight line between them. And use those points. Are you listening at the back there? Guys at the back? So, same thing as what we did before with a straight line. We cast our values down, and that will work. That will give you a method. Okay, the only problem is that gradient there is probably something like that. That's a bad drawing. And basically, it's like this. If you've made a chord there, one gradient's going that way and one gradient's going that way. So in other words, it's fairly inaccurate. And the solution is what we were talking about earlier, how far apart the points are doesn't matter. So what they did was, let's say we call this Q. You just bring Q further and further down and bring it towards P. Okay, and you get closer and closer. Now that's going to give you a more accurate line, isn't it? Now what happens when it gets to 0?
0. It's the same.
Q gets to it, it's going to be the gradient, it's going to be you have got a difference, but if you're getting towards 0, then you do have a difference. And what they did mathematically, and you can look the formula up, I'll show you it later actually. So you can look at the maths they did and how they worked it out from first principles. And basically it's quite straightforward. They just tended this down towards 0, and then they found the solution. Okay, and what they got was this. The beauty of this solution is it works with any value of x. So what they got was this. What we're saying is you make that distance smaller and smaller, and we call that, initially it's called this delta x, small change in x.
Over delta y.
Huh?
Over delta y.
Sorry. Right, and that's basically become this dx, sorry. So that's become dx, small change in x. Now what was the formula for finding the gradient?
Shut up, man.
You listening? So our formula before for that, you remember our formula before? It was all to do, that's a 2. It was all to do with the difference between y2 and y1.
Changing x over changing y.
That's it, the change in y over the change in x. That's spot on, is that?
X1.
So if we make that really, really small, we can get a precise figure. And mathematically that's what they did. So they said that finding that gradient, so if y equals x squared, the gradient, the change in the y divided by the change in the x, gave them this answer from first principles. Okay? You right with that? They also found that if y equaled x to the 3 dy dx, so this is what we call the differentiation. This is the solution, and this is what you're going to be doing shortly. If it was x to the 3, then we got 3x to the 2. Okay? Then from first principles, if y equals x to the 4, does anybody want to tell me what the answer is? Can you spot the pattern?
4x3.
4x3, very good. 4x3. And so it goes on. Do you all see what happened there? So x to the 4 became 4x to the 3. So if this was 5, it becomes 5x to the 4. That's why I said about taking 1 away from a number right at the beginning. All you've done is taken 1 away. Well, the first thing you do is you take the power down to the front and multiply it to what's ever in the front. What's in the front of this x?
4. 1.
A 1.
Oh.
It's 1x, isn't it? We don't put the 1 in, it's 1x. So 4 times 1 gives you 4. Take 1 away from the power, you've got 3.
Alright, so it's always 1 minus from the...
That's it. Take down to the front the power, multiply it, take 1 from the power. Okay, if there's a number in front...
Well, if it gives us 2y equals x4, then we times 4 by 2.
Right, yeah, that's where we're going. Let's say this one. What would that become? Doing our differentiation on it, solving it for differentiation. What was that?
It would be 8x.
It would be indeed 8x, what was the number?
3 to the power of 3.
Yeah, you're right, 3. You're right first time, 3. You see what's happened, everyone? Have you got that? So I told you it was easy, didn't I? And I wasn't lying, it appears, for the change. So the power comes to the front and multiplies whatever's in the front. And then we take 1 from the power. So that's it now. That is differentiation. It's that simple. Yeah, okay, but what does it do for us? Well, that means that you can find the gradient at any value of x if you've done this. So if I want to know what the gradient is when x is 2, I put 2 into there. So when x is 2, then we've got 8 times 2 to the 3. So 8 eighths. 56? 64. I'll have to edit that on the video, won't I? Right. Okay. So that's the gradient when x is 2 if that was your formula. So if I drew a big graph of this formula, x to the 4 and then times it by 2, and I put 2x as 2, went to that point where x is 2, and did all the triangle trick and all that, and if I did it on a real piece of big graph paper, and I could, or did it on software and I could zoom right in and find the gradient, I'd find it was 64 at that point. Okay? So that's your starting point.
Let's say we have 2y, you know, like right at the start where we put y equals to x. Would we ever get like 2y? Would we?
You mean we'd have 2y equals 2x plus 4, 2x to the 4?
Yeah, would we?
If you got that, you would have to rearrange it. You'd carry the 2 to the side, you'd divide through by 2.
And then,
and then it gets simple. It actually gets easier. Yeah. Yeah, you'd have to rearrange it to make that work. You could end up with that situation to start with, but when you've manipulated it to suit yourself, then it gets easier.
Yeah.
Okay? So anybody struggling with that at all? Dead easy, yeah?
Dead easy. Why did you say it?
Right. Let's just...
Can you do another one like this?
Yeah, we're going to do a few. We're going to do a few, don't panic.
I'm not quite grasping it.
Right. Let's start with a few easy ones. Go back over here. We'll all do it together, and then I'll give you some harder ones, and then you can have a go at some. Okay. What about, let's just start with an easy one. So that one. So, the guy back in blue jacket, you're chatting a lot, so you must have this nailed down. What am I going to do first?
Come on, do it.
Start with looking at the power. What's the power?
Go on, Lily.
X is 1 4 times 2.
Well, this is x to the 2.
And you do 4 times 2 like this.
Does that look like a 1 there to you? That means you need to sit at the front.
So then say 8x.
Right, what happens with this 2 here?
You times it by the 4.
Times it by the 4, so I've got 8x, and what happens to this? Take 1 from it, so it's not gone. It is gone, in the sense of it doesn't have a power. It does have a power, but it's not one we tend to write. It's to the 1, but we don't tend to write the 1. We tend to just put 8x. Doesn't hurt if you do put it there, it's totally correct. Go on, here's.
Would we ever get the power to like -2, let's say?
Right, let's have a look.
So that'll just go to -1 then?
Let's have a look. Y equals, let's just do an x to the -1. Okay. Now, x to the -1, does anybody know another way of writing that? Laws of indices. Think of the laws of indices.
1 over 2.
X plus 1 x -1.
1 over x.
1 over x, yeah. All sorts of answers there. Can be written like that. You recognise that that's identical to that? So when you get something like that, to do your differentiation, you need to change it into something like that. So you can do your differentiation on it. Yeah? So we've got that. What would be the answer to that one? It's the same method. It looks hard, but it isn't. It's the same method. Take the -1 to your power, divide what's in front of it, which happens to be a 1, because we haven't written anything, so it's 1. There's always a number in front of the x. If it's not, if it's 0, well, that's a number as well.
If there's nothing there,
they would disappear anyway. So it's always a number of something in front, and if it doesn't tell you, it's a 1. So you've got a positive 1 in front. What's positive 1 times -1? -1, yeah. So it's minus. I'm not going to put the 1 in.
Would it be -x then?
What's -1?
Add 1.
-1.
Minus
You always take 1 away.
Oh no, it'll be 0 then, isn't it?
-1. Take 1 away.
-2.
-2.
-2, yeah.
Any advance on -2?
1.
1 is
1.
2.
I don't know. -1.
It's funny, you know, when you challenge people on that, they always start to doubt.
It's already minus, you take it.
Yeah. It's 0 then, isn't it?
It's 1.
No, it's -2.
It's 2. -2.
Right, -2.
Yeah, that's what I said.
Told you.